Welcome to Easy Academic. In this episode, we'll be going over vectors, their definition, different forms of notation, and simple properties of vectors. So firstly, a vector is a mathematical object that's said to have a direction and a magnitude. So what this means algebraically is that, say we have a graph. If we create a two-dimensional plane with this point, 0, 0 as the origin, then we can say that a vector is sort of like an arrow, points in a specific direction, and it has a specific length, which we'll call its magnitude. So if we call this vector A, then we'll have coordinates uh, x, y. So we can notate A as A equals x, y. This is likely the notation you're going to see if you're just referring to coordinates in the Cartesian plane. However, with vectors, we are more likely to notate it in this sort of column-like way. So you'd see it as x, y like this, where you'd have the first entry on the top, the second entry below it, and so on. And in three dimensions, you'd have something like uh, x, y, z. So let's now take the example of a vector q. Let's say that vector q is equal to uh, 2, 3. So how would we notate this on this graph? So first we'd find its x-coordinate, which is 2. So 1, 2. And then we find its y-coordinate, which is 3. So 1, 2, 3. And then we'd know that the vector starts at 0, 0 and ends at 2, 3. So we'd have something like this. So this is the vector 2, 3. Let's try now moving this vector around. So let's say we move this vector 2, 3 and start it at 0, 2, or sorry, 2, 0 instead of 0, 0. You'll notice that this vector is, it's functionally exactly the same, but we've changed where its origin location is. This is still fundamentally the same vector, but we've changed where we started it from. So does changing the vector change the actual value of the vector? The answer here is no. Let's look at some other examples. Let's now start with a vector A, which will make equal to 1, 4, and with a vector B, that will make equal to 5, 5. So if you're following along at home, I'd like for you to create your own plane and try to draw where these vectors would appear. So you can pause the video to try to figure that out. Okay, so first we'll start by drawing the vector A. And let's draw this vector A in blue. So if we have vector A in blue, we'll first start by finding the x-coordinate, which is 1, and then the y-coordinate, which is 4, and we'll observe that it starts at the origin. Just in the standard vector notation, we always start at the origin, and it ends at this point. So the vector points in this direction, and it has this length. If we start with vector B now, which we'll draw in red, we'll observe that it's at 5, 5. So the x-coordinate is here at 5, and the y-coordinate is here at 5. So we'll have a vector that looks something like this. Next, we're going to look at some alternate notations of vectors. So you might see vectors, as I've shown them, in this sort of column description. So for example, let's take this column vector 5, 3. Some people might write this vector as 5, 3, sort of similar to how you might see standard coordinate notation. Both notations are more or less valid if we are attempting to display something in a plane, but you'll see in future episodes why it's more conventional to write your vectors in this way. But just know if you ever see it written like this, you can still represent it in 2 dimensions if you treat, again, the first entry as the x, second entry as the y, or in 3 dimensions, you'd have the third entry as the z. Next, we'll be talking about vector magnitude. So the magnitude of a vector, as I earlier stated, is the length of the vector. So you might be asking, how do we compute the length of the vector? Well, let's say for example we have a vector A, and we'll make its value equal to 3, 4. So if we were to draw this vector out, we'd have x is 3 and y is 4. So we'd have a vector, let's draw it in red, and we'll have it look something like this. Now you might observe that thanks to the Pythagorean theorem, we could find the length of this line by finding the x-coordinates squared and the y-coordinates squared. So the magnitude of A, which is often denoted as with two lines, so this is how we say magnitude of A. Magnitude of A is equal to the square root of the x-coordinate squared plus the y-coordinate squared. So we'd have 3 squared plus 4 squared. And for the astute among you, you might observe that this is a 3, 4, 5 triangle. So we'd have that the magnitude of A is equal to 5 units of length. Let's take another vector, which we'll call vector B, and we'll make it equal to 2, 2. So if we were to draw out vector B, we'd find that in the x we have 2, in the y we have 2. So it would look something like this. If we now wanted to find its magnitude, and you can pause the video to attempt to find it yourself, we'd find that the magnitude of vector B is equal to the square root of 2 squared plus 2 squared. This is equal to the square root of 4 plus 4, which you'll observe is just root 8. So some instructors might ask you to find this exact value using a calculator. Others, in the case that you might not have a calculator, would just ask you to leave it in the form of a rational. So you could even simplify this further and find that it's equal to 2 root 2. Before we move on, I'd like to point out one more notational nuance that you might observe, and that is oftentimes when we denote vectors, we denote them using an arrow on the top of them. So throughout this video, I've been referring to vectors like A and B, just using the letters A and B. Since this is a linear algebra tutorial, it should be assumed that anytime I refer to any letter or any arbitrary value as a vector, it just is a vector. But if you were to see a letter or some other character with the arrow on top, it's safe to assume that it's a vector in most mathematical contexts. Finally, we'll talk about the concept of a unit vector. So the unit vector is any vector. Let's create a new vector and let's call it C. The unit vector is any vector where the magnitude is equal to 1. So C is a unit vector when the magnitude of C is equal to 1. So let's show an example using the 3, 4, 5 vector. So if we take the earlier vector, which we called A, and we have its value as 3 and 4, as we earlier proved, the magnitude of A is equal to 5. So if we wanted to make this a vector, be a unit vector with magnitude 1, what we do is we divide this vector by 5, because 5 divided by 5 is 1. So when the magnitude is 1, we simply need to multiply the vector by that same value we multiplied the magnitude by, which in this case is just 1 over 5. So if we now took A, 1/5 A, we made it equal to 1/5 3, 4. This is now a unit vector, because as we can show, the magnitude of 1/5 A is equal to 1/5 times the magnitude of 3, 4, which we already know to be 5. So the magnitude would be 1, and it's a unit vector. The final thing I'd like to show you is the standard basis vectors. And so what a standard basis vector in this context is, it's a unit vector that we can use to describe standard axes, such as in the xy plane. So for example, if we take the standard basis vector I, which we'll denote here with an arrow, we can say that this vector is equal to 1, 0. So that's 1 in the x and 0 in the y. Let's denote it using the color red. And that's what the standard basis vector I looks like. You might see this in physics or in calculus, and just know that it's used to refer to this vector, which goes 1 in the x direction. Let's denote now the second standard basis vector j, which is equal to 0, 1. And again, this is equal to 0 in the x and 1 in the y. So it would look like this. In higher dimensions, such as in 3 dimensions, you might even see a standard basis k, which would be notated like this. And note that since it's in 3 dimensions, you'd have 3 entries. So you'd have 0, 0, 1, and this would be a 1 in the z. And so this has been an introduction to vectors in linear algebra. Please like and subscribe to the channel. If you have any questions, be sure to leave them in the comments. And if you have any further topics you'd like me to cover, be sure to leave that in the comments as well. Thank you.